Саша, ты пока только экран показываешь или уже говоришь что-нибудь?
No, no, я ничего не говорю пока. Ну и
Окей.
даже на экране ничего не написал. Но сейчас
Окей, окей.
начну. So I'm just. So I think I will start with what I said last time, the inequality with the slalom game, and then it was something which was more or less completely proven. At least I would like to believe in this. And then I'll try to make some corollaries. And first, this Barmpalias, there are two main corollaries: the constructive ergodic theorem of Huygens and the Barmpalias Lewis-Pye result. So let me try to start. So the inequality we had last time. So imagine we have some family of gates of some length L1, L2, Lk. And then for every point xy, and also we have some two numbers, alpha and beta, which are the minimal and maximal slope of a curve. And then
Sasha,
for every point
and
xy,
gates are parallel to each other, right?
now gates are vertical, all gates are vertical. And now for every x, point xy, we consider the curve which goes between alpha and beta, with slope between alpha and beta at any, no, it can move something like this. And minimal number, so let me write it again. T of xy is the minimal number of gates crossed starting from xy and moving with speed between alpha and beta. And then we consider function t of x, which is maximum over x or over y, t of xy. So for every vertical line, we choose the point when the slalom player position is the worst. There are many. She's forced to cross maximal number of gate. And then the bound, that's the integral of t of x for x, all x is in R, is bounded by sum of length divided by beta minus alpha. This is what can be called Misha-Andreev crossing lemma. And the question, it was proven by following, I just can say, remind that we consider the function as this function t as a function of y. So it's a function tx. And we consider the integral of tx as a function of x. And then we looked how this integral changed when we decrease x. And if we cross every gate, it increases by some things, and then it starts to decrease. And the bigger is this function t, the bigger it decreases, the faster it decreases. And so, since we start at 0 and end at 0, the total increase should be equal to total decrease, and we have bound for the speed of decrease and so on. So, is it okay, this thing? Bruno or Kolya or Misha, or what this, at least this part, convincing?
Very convincing.
Yeah, Misha, if you agree, we will switch to the next part.
Yes, I agree.
Yeah. So this.
Since that I understand now the proof.
Yeah. Okay, but now there are two steps. First, imagine that we have the gates not vertical, and we want to get some bound for the crossing number for these non-vertical gates. And the idea is that if you cross a non-vertical gate moving with speed between alpha and beta, then you are forced to cross some vertical gate. So let's draw it in red, alpha and beta. Namely, just let's. So if you cross this thing somewhere here, you need to go farther. And so if you put just alpha and beta thing here, and then this gate is necessarily be crossed if this gate is crossed. So this crossing implies this crossing. And this is a bit bigger thing, but at least it's the thing is big O of let's say of length of the gate, and the constant depend on alpha and beta. No, the vertical part is just smaller than the length, and this addition is bounded by alpha and beta times the horizontal part. So this is the total thing is just a constant times bigger than the length. This is one thing.
But
so if we have
in one direction only, because you can cross red vertical gate without crossing this slope gate.
In one direction. So I say that there is a function tx, t of x, for vertical crossing with new vertical crossing. But I am saying that t for horizontal, for a real with not vertical one, is smaller than this one. And so if we want to get a bound for the function, for this function t of x for non-vertical crossing, we can replace it by vertical crossing here. And of course, this implies some increase in length, but it's a constant increase. Или я не на правильный вопрос отвечаю?
No, yes. You are right. We need, if we are interested in upper bound, it's okay.
Yeah, only in upper. And the next step is even more important because it's only an upper bound. So now imagine the gates are not vertical and follow a polygonal broken line, Lomane, polygonal line. So the gates are doing something like this. And then if we have this alpha beta, I don't know how to say it, angle or cone, then is some thing which is number of let me say bishop crossing of alpha beta cone. What is this? It's just the number of times when we go from this below zone to up zone. So here is just one. If we don't reach the up zone here, we go in the below zone and go to the up zone and then never return to below zone. And if it will be a bit bigger, it will be 3, because we once crossed the zone from below to from bottom to top, then from top to bottom, and then again to bottom to top. And there is obvious thing. The number of bishop crossings is the lower bound for a number of slalom crossing, antislalom slalom crossing. Because if our slalom player goes everywhere inside this thing, he is forced for each part of the line which goes from below to above, and there is at least one crossing. And this is O alpha beta of total length divided by beta minus alpha.
Sasha, can you repeat the argument why this inequality is true, the first one?
But is it clear what is bishop crossings?
The bishop crossings is the number of times this blue line goes from below zone to up zone, or the other direction.
So now this blue line is divided into parts, and each part go from below to up, or to above, or from above to below.
All right.
So for each part, the slalom player should have at least one crossing.
Why?
Because the slalom player is confined to the zone between alpha and beta.
And why is this?
No, it's by definition. The restriction for slalom player is that every point the speed is between alpha and beta. So if it moves with minimal speed all the time, it will go this line, and if it moves with maximal speed all the time, it will go this line. So it's actually won't help if at some point he makes a fast movement, actually, even. So he cannot avoid these things anyway. But if the momental speed, if at every moment the speed is between alpha and beta, then the average speed is also between alpha and beta, and we cannot go out of this line, and we are forced to move from left to right, and everything of this. It's kind of geometrically obvious that just if something goes from below to above, then one crossing is guaranteed because of kind of Jordan curve theorem for polygonal lines, or for whatever. So this is what, and this is called
Sasha,
bishop.
But wait a bit.
Yeah.
In the right-hand side of the second inequality, you have some integral. And in the left-hand side, you do not have any integral. So why this the second inequality?
No. Of course, I am writing not when I write like these things. This is integral of over x max over y, and this is also integral over x max over y.
Where xy is the starting point of the
where xy. So this is a function of xy, and this is another function of xy, and then we take what I didn't write here, and it was my omission. So first we should take the maximal over y, and when should we take integral over x? So we are actually interested in our integral over x, maximal over y, this t bishop of xy. When bishop crossings are this new kind of crossing, or actually old kind of crossing before Andreev. And so we get the bound for these things. So is this clear? Bruno, you are not happy. Say something. Hmm?
Yeah, it's clear.
You're still not happy. Happy people have a different look completely. Uh, something bothers you. Just tell me what is bothering you.
Well, there is a maximum and integral, and somehow it's a lot.
No. There is a function of two variables, f of x, y, which is bishop crossings, and another function which is not bishop crossings, g of x, y. And this is true for every x and y. For every position of x and y, the number of crossings from up above to below and back is just the upper bound for the number of slalom crossing. So slalom crossing and bishop crossing. No, something is not
Okay,
clear.
okay, so you didn't speak about maximum yet.
Not yet. This argument was just comparing this to quantities for a given point x and y. The first quantity is how many times the curve goes from below to above and back.
Yeah, but you still
And the
use
second
the
times is the
inequality.
minimal number of crossing that the slalom player will make with the curve when moving with the speed between alpha and beta.
Yeah, but in the
And
bottom you used
the
the
slalom crossing is
inequality.
bigger.
Yeah, but you used the theorem, so or the
No,
uh,
so let
slalom
me say,
lemma.
so if it's true for every x and y, of course it will true for maximum over y.
Yeah, but this is a
And
huge
if it's
waste
true for
to.
maximum over for every x, it will true for integral.
Yeah, I agree, but how can you waste this maximum?
No,
You use a crazy extra maximum of y, and
yeah,
so you can prove something non-trivial by taking such such an imprecise upper bound.
yeah, I take a maximum of y because that's no, I prove that this integral of this maximum is small, which implies that integral for every whatever y I take as a function of x, the integral of x of fx and yx is small. We will need it only for some y's, but what I am proving is just the integral over maximum over y.
Yeah. Yeah. So this is very counterintuitive. So I have the right to be a bit troubled.
No, it definitely it's your legal right, but if there is nothing special. No, the idea is that we need the bound for this maximal value. We need the bound
Yeah.
for an unpredictable point.
Yeah.
And then we use this for this point, we use the one what we have is a bound for a maximal value, and this is more than we need.
Yeah. Okay, but everything is clear now.
Okay. And now there are two things which I can derive from this. First is Birkhoff ergodic theorem, and second this Barmpalias Lewis-Pye result. And I hope sincerely that I can do both things. And the question is what you prefer to start with. What should be first? С чего начать? С эргодической теоремы или с Бармпалиаса?
The easiest thing you should do first.
Okay, they are both easy. But okay, since it's a classical theorem which doesn't involve any computability, by definition, it should be considered as something easy. So let me start with Birkhoff ergodic. Oops, Birkhoff ergodic theorem. No, probably we need this. Okay. So what is Birkhoff ergodic theorem? Imagine we have some space X, space with measure. And imagine we have some transformation T, which it maps X to X and is measure preserving. And there are two classical examples. First example, X is a circle, the окружность, circumference, not the disk, but the circle. And T is a rotation by some angle alpha, preferably a rational one, but theorem is true for any case, but it's interesting for a rational one. And the second example is, which is called Baker's transform, преобразование Пекаря. So x is 0, 1, and t of x is 2x modulo 1. So here we just rotate a circle, and here we just increase this twice. Like, I cannot say it in English, we're раскатываем тесто. We make, like a baker, we make a longer thing. And then we cut this longer thing, and then we move this part here, which is taken modulo 1. And we get something which is called, in Russian, it's called Napoleon's cookie, and in French it's called more neutral millefeuille, 1,000 leaves. So this is the transformation, or just if we consider just in terms of digits, this means that we just delete the first digit. And I hope, more or less, that what should be clear now is that what are this transformation, and measure this as uniform measure on a circle and on an interval. What should be more or less clear that indeed they are, this transformation are measure preserving. So in other words, if you take a random variable which is uniformly distributed in a circle and rotate it, it is still uniformly distributed in a circle. Or if you take a random number in 0, 1 and then delete the first digit, it's again a uniformly distributed number in 0, 1. So Bruno and Misha, is it okay or not?
Okay, measure preserving, it's clear.
Measure preserving is clear. And then what it says Birkhoff ergodic theorem. Imagine there is some function f, which is, let's say, bounded integrable function on x. And then we can consider a value of function f along some trajectory, f of t square x, and so on, and take some average. So here does it mean we have some function on a circle, and we look at the values of this function in an arithmetic progression of the point of the circle. Something like this. And here we look at the value of the function on this point, on this point, on this point, on this point, and so on. And Birkhoff theorem that say that this limit as n goes to infinity exists for almost all x. By the way, there is some kind of standard classical proof of this Birkhoff result using some measure theorem. Does anyone know this proof? I heard it many times, but always forget it. Кто-нибудь знает, как это доказывается обычно в теории меры? Definitely we had it in some courses, but it was long ago. But никто не помнит?
Нет.
Okay, then and what I'm trying to do is prove Birkhoff theorem using Bishop's inequality.
Вот очень странно. It's very strange. At the first glance, they seem to be completely unrelated. I mean, this antislalom game and this limit.
No, it's not anti-slalom game, but more this Birkhoff intersections.
Okay,
but still,
also Birkhoff intersection.
Okay, let me try to explain you. So what we would do what we should do is just what is this limit? We start with 0, and then we move by f of x. And then we type here, we have add f of t of x. And
But
then we
what
have...
are your legs? I mean, the first leg is 1.
I start with any point. The picture depends on x. Some x. We start with 0, and then we add f of x, and we add f of
so
x.
the length of your leg, I mean horizontal leg, is x, the first one.
No. The length is 1. Here it's
1.
just 1.
Uh-huh.
No, I want to geometrically represent this ratio. And for this I draw the curve.
And the length of the second leg is f of x, right?
The vertical length of the first length is f of x, and the second is f of t of x, and the third is f of t of x, and so on. So I just take these things and consider them as a vertical increases along some polygonal line.
And then you obtain your ratio is the slope. Just the slope.
The ratio, of course, the line, let me draw it some symbolically. It goes something like this. Okay, let me try draw it better. So it goes somehow like this. And the final ratio is the slope. So this is this slope. And let's consider x for which slope crosses infinitely many times the interval alpha beta. So we need to show that this slope has a limit. Of course, this depends on x. For some x, it has a limit. For some other x, it doesn't have a limit. But for each alpha beta, we consider the interval when the slope crosses this interval infinitely many times.
But your curve depends on x, right?
Yeah. So we consider x for which this slope crosses infinitely many times. And if we prove it that this is a null set, then we are done. Because the set of all x for which there is no limit is a union, is covered by the union of all these alpha beta sets for all rational alpha and beta. In other words, there are several reasons why the sequence doesn't have a limit. There are, for every pair alpha beta of rational number, there is one specific reason. This is because the sequence crosses the interval many times, infinitely many times. And if for every reason the set of things which where it happens is zero null set, then in total we also have a null set. So, ну чего, is it clear?
Up to this moment, it is.
Yeah. So, Bruno, are you okay with this?
Everything you say is clear, but the start of the proof is very counterintuitive.
No, the start of the proof, the reason why a sequence doesn't have a limit, actually it's a bounded sequence, because the function is bounded, then the average is also bounded. So for a bounded sequence, the only reason why it doesn't converge is that there is some interval that is crossed infinitely many times.
Yeah, this is completely clear. So
Yeah.
you can continue.
Yeah. And the question is why this thing has why it's a null set. And the idea is that we need a bound of the set when of the set of all x, and there are at least n crossings. So if we have bound for this set, then the set of where are and these bounds converge to zero when n goes to infinity, then the infinite crossing is the intersection of all these sets, and so it's a null set. Yeah.
Mm-hmm.
And now, up to now, we didn't use anything. We didn't use that the sequence is measure preserving. But now let's try. So let's consider the number of crossings as a function of x. How to say it? Sorry. And what is most important, at what is C of f of x? C of f of x is just the same, the crossing of the same curve, but started here.
Sasha, this is not clear.
Yeah.
Wait.
Okay,
Wait, move it again. So x on your picture, x is used just to compute this first vertical leg, right?
Yeah.
So
if we just make an assignment
Sasha, instead of f of x, you will have f of x, as I understand, right?
No, if not f as a function, there is transformation t.
Sasha, maybe you meant t of x and not f of x here.
Oh, so yeah. Sorry. Of course, t of x. Yeah, stupid. Sorry.
And above also, c of t of x.
C of t of x, of course. Sorry.
And also you need to start, I mean, the slope will be also, I mean, this slope will start at this point above.
Yeah. So initially we start with the angle alpha beta angle started here. And then we start with the alpha beta angle started here. And so on. And what is important is that this c of x and c of t of x are just different by the transformation of x. So the integral over x of the things is the same.
Because the t is measure preserving.
Because t is measure preserving. So t of x is distributed in the same way as x, so the expectation of c of t of x is the same as expectation of x, c of x. And then, so we can consider something like this. We can take c of x plus c of t of x plus just m times. So we want to get a bound for this integral.
So wait, why do we care about this integral?
No, we care about this integral. We go in another direction. We care about this integral, but this integral is equal to this integral. And so it's enough to get a bound for this integral.
But wait, and why do we care about the first integral of c
Because
of x?
we need a bound for the places when the function c is great. So we are interested in the bound of the measure of the set when there are at least n crossing.
So what's again the definition of c of x?
C of x is the number of crossing, starting from if we start with x.
Sasha, you should tell us whether you plan to, are you going to prove there is a bound for at least n crossings, or are you going to get this as a byproduct of bounding the integral of c of x? Is this your plan?
I will get it as a bound product for getting the integral of c of x.
So in fact, you're not going to give a combinatorial proof with like something a function of n. You're just going to prove that the integral of c of x is bounded. And from this, you will directly get that the thing with infinite has measure 0. So in fact, there is really no, okay. So this is the plan, is to just find that the integral of c of x is finite.
Yeah.
Good.
And then so it's a kind of, we should be a bit more careful maybe in the limit transitions, but let me explain the plan. So why we do all these things? Because these things are exactly the number of crossings starting from different points. It's exactly the integral which is estimated by Bishop-Crossing inequality. So here let me draw. There is a curve. This is a curve of consisting of the things, and then for every point we look at the number of crossing.
What is this curve? Define it.
It is just curve like that one. It's just 1, 2, 3, and here is f of x, and then f of x plus f of tx. It's just this exactly this curve.
Okay. We draw
but this is just drawn in a smaller scale, because now we consider not only this big curve, but also we consider the curve starting from every point. Not every point, but with points starting from 1, from 2, and so on.
Wait a bit. So you consider the integral, right? So
yeah.
x ranges through your space capital X, right?
Yeah, x ranges. Yeah.
So you are talking now about C of x and not C of t of x. Just the first.
No, here we speak about C of x integrated over the measure on x.
Okay, good.
But and here also we consider the integral of t of x, of C of t of x with the measure on x.
Okay, so that means that we take.
And it's exactly the same integral.
Yeah, I mean the integral is the same, the value is the same, but the interpretation is different. We take a random point, make one shift by t, and then
and take c, the function. And then take f, and then take the number of crossings. But so these integrals are the same. And so we can consider the sum of these integrals, which is the sum over different points of the curve. And this is a way to get connection with Bishop inequality. So before we have something about the curve at point x, but now we can say that instead of taking the average, we can sum this function as function of x and point x and point t of x and in shifts, and this will have the same average. But now this is an average of Bishop type, which means that we consider the number of intersection starting from some points with different, which starts of 1 and 2 and 3 and so on.
Right.
And so this are as bounded. No, let me for now ignore the change of integration order. This is bounded by this is the sum from 1 to n, for 1 to m, of a function of a Bishop type function, which is the maximal number crossing at point and point e I. So we are interested in crossing that start here. But instead of that, we can just take a maximal value over all positions of this vertical positions.
But what about you have a problem here. E ranges through natural numbers, but in the inequality, you integrate overall real numbers.
Yeah. But it's not really important, because if we take if we go from I to I plus 1, just there is a question whether we intersect this line, but this is just one or more or less one plus or minus one intersection. But for the other part, the intersection, if a slalom person starts here, then it should go through some point here. So if there is a good way to start here, then it's also a good way to start here. Since our curve is made of segments of length 1, then the value of the number of intersection doesn't change. This function t doesn't change significantly when on the interval between I and I plus 1. This function t differs at most by 1 compared to the value of t of I and ti plus 1. It is just the question of crossing this specific part. And then since we are interested in the integral over x, the plus minus 1 thing is not important. And the more or less to finish the argument, we observe that if we divide such a thing by m, we get a variation of our curve, the total length of all the things, O variation curve divided by m. And since the f is bounded, the total length of this curve is big O of m. So this is O of 1. And so we prove that this integral is finite. This is the scheme. And I can say what kind of the argument I try to avoid. Actually, there are some limits we take. We can increase the length of the curve, and also so this m goes to infinity, and the length of the curve goes to infinity, and we should be careful in deciding how much it goes to infinity. But maybe before going into this detail, we should understand the general picture.
Yeah, can you repeat the general picture, please? I didn't get why integral is finite.
Okay, so do you understand the integral of what we consider?
Yes.
So for every x, we have a curve. For every x, so if we have x, we have a curve. And then we count the number of alpha beta intersections starting from this point of the curve. And this is C of x.
Yes.
And I want to get a bound for the integral of C of x. And this is difficult. And for that, we say that there are also C of tx. And it has some other integral, C of tx, which is the same because t preserves the measure.
Yes.
So we have several functions, C of x, C of tx, C of t square x, which all have the same integral.
Yes, this was clear.
And we need the bound for the integral of each of them.
Yes.
And the idea is that we note that the sum of this function, c of t square x and so on, is bounded. And this will give a bound for an integral of each of one.
Yeah, but then you use that total variation of f is bounded. But you say
and total variation is proportional to the length of m, more or less.
Oh, sorry, yeah, because f is bounded. Oh, sorry, okay, it was clear. Yes, sorry, the last step. Okay, yes. Okay, now it's clear. Sorry for. Okay, so now I understand why the sum is bounded.
Sum is bounded, and the bound is proportional to m. So the average is bounded by some constant. So this is again general scheme.
Okay, and so now, okay, I get it. And now only why can we flip limit and integral?
Sorry?
So the last part of the proof is why can we flip limit and integral over x?
Yeah, so now we need to be more exact about, because actually in our bound for bishop we did this finite number of gates, and here we have infinite number of gates, so the numbers of crossing can be infinite or something like this. But I want the general picture to be clear. Let me say like this: we need to estimate of integral of some function c. Our idea is that we rotate this function in several ways, in such a way that sum of this all rotation is for some reason bounded, small, not too big. And then integral of each function cannot be big, otherwise the integral of the sum will be big. And the sum is bounded. We know that they somehow match each other, so each of them can be rather big, each function. But when we sum of them, the points when they are big don't overlap much. Сейчас. Коля, Миш, скажите чего-нибудь.
Нет, ну я вроде все понял. Мне кажется, никакой проблемы с пределом здесь вообще нету. Когда мы доказываем ограниченность интеграла, мы можем просто, я имею в виду от исходного, взять достаточно большой отрезок и ограничить константы, не зависящие от длины отрезка. Площадь, правильно? То есть,
примерно, сейчас.
Берем достаточно большое m и доказываем ограниченность некоторой абсолютной константы вот того, что ты написал. И вроде это доказал.
Да. Сейчас, Миш, понятно это или надо что-нибудь... Я как-то запутался, мне самому не нравится, что я рассказывал.
I'm slow, so I don't understand all details, but it looks clear enough. I don't understand another thing. You have started from formulating, saying about constructive proofs of ergodic theorem, but this proof, why you say this proof is constructive?
No, there are several levels of answers. First of all, now we cannot claim any constructivity because we don't make any assumptions about the computability of f or computability of t or anything. So this we make a classical proof.
It's just a classical proof, slightly different from something.
Yeah, it's just a classical proof.
Okay.
But why it's good for Bishop and good for Huygens is that if we assume that in some reasonable sense t is computable and f is computable, then the number of crossings is more or less a computable function of x. And this C of x is more or less a lower semicomputable, the computable from below function of x. And it has, and we have a bound of integral. So we know that the set of places when the function is greater than n is smaller than constant divided by n. And this is exactly what is needed to show that something is not Martin-Lof random. No, it's a kind of technical things because we need to go into the definition of Martin-Lof randomness and so on. But the advantage is that somehow the bound is constructive because the bound of the measure for the bad points is...
Sorry, you have several things. You have transformation
T
preserving measure, and this transformation is also computable, yeah?
No, we need to assume that it's computable in some way.
Okay, and f is computable.
F is somehow computable also.
And you claim that C of x is also computable.
C of x is not computable, it's enumerable from below. So which means that we can increase it, get a bigger and bigger approximation that converge to C of x.
So sorry, yeah. And is it good for integral? We need a bound of integral.
No, this is a monotone convergence theorem. If we have a bound for the limit, it's the same. If a function is a limit of increasing sequence, so the bound for the limit is the same as the bound for every term.
Yeah. These functions are non-negative. Or...
Yeah. This is completely safe in terms of Lebesgue measure theory. And the bound is just a bound. It's not something classical or constructive, just a bound. But the function itself is approximable from below. So the places when the function is greater than n, this is they can be enumerated a set of, we can enumerate the intervals which form together these places. And so we can cover our set, but covering our bad set by an effective cover which has measure less than constant divided by n. So this is the computability part, so to say. Okay, and returning to this estimate, let me say what Kolya already said. So we need to get a bound for function C of x. And to get, of course, the C of x is maybe infinite, but its limit, if we consider Cn, if we take crossing only over n things. And it's enough to get the same bound for Cn. And to get this bound for Cn, we get this, take m is much bigger than n. And so most of the crossing will still happen inside the interval between 1 and m. So we can apply it to... Okay, we can consider the interval, if we're looking for the crossing in the first period, then we take an average, if we want to have an average for this, we take here m plus n minus 1. And then divided by n, but if m is much greater than n, it doesn't matter. So this is kind of some simple bound. We should do it in the right order.
So you mean n is much bigger than m?
No, we need m is much bigger than n. Here the average.
So what is big n? N is number of gates you consider. So you...
n is number of not number of gates. it's n is an interval when we are worrying about crossings.
Yeah, and it should be much bigger than m.
No, vice versa. Let me see. So what we do, we consider this n crossings. We consider this crossings which happen at C of x. They happen from 0 point up to n. And the next step, they consider crossings which happen from point 1 to point n plus 1. And so on. So in total, we have so the part of the curve which is relevant to us is from 0 to m plus n.
Okay, sorry. Yeah.
So we have here O of m plus n divided by m. So for that we need, no, for example, we can take m is like the same n or 2n or whatever.
Okay.
But m should be big. M should not be too small because if m is small, then we divide. Here we have a bound in terms of m plus n, and here we divide it only by m. Oh, I seem that I confused everyone. But
I think everything is clear what is said since the start.
But it's a pity because it's a very simple thing and it's just me who cannot present it in a convincing way. But ну что, Коля, понятно это, нет? Is it clear or not? Not really.
No, it is clear.
It's clear, yes.
And this is what once I told about Huygens, I think once I spoke about this, about Huygens proof of Birkhoff theorem, effective Birkhoff theorem, and Huygens proof was just the idea was they consider this function not for all the crossings, not for all points, not for all inequality, not for maximum over y, but we take only things along the curve. Then there is another estimate using this something which is called cumulative sum, and this is another tool, but I think now that it's more complicated and less intuitive than the general thing. And actually, there are two papers of Bishop. In one paper, first paper, he considers this general argument, but with some complicated proof. And I sent it to Sasha Kazachinsky and to Misha, and in 5 minutes, they cannot explain what is there. And this, since I think that clear proof should be clear in 5 minutes, so I claim this is not clear. But if anyone can explain you what is written in Bishop, it would be a special thing, interesting things. But okay. Okay, so if everything is clear, then I can try to use the rest of the time to show the Barmpalias argument.
Okay.
Okay, so let me try to.
So sorry, I need to go. There is some problem. Yeah. So I will watch the recording.
Okay, I can provide a special session for you if you. In this way, I can be sure that you didn't avoid this. Okay. Why it doesn't?
No, I will.
Yeah. Why it doesn't want to? I want to take this, make it. And I want to erase everything. Why I cannot do this? Oh, I want to erase everything. Oh, good. And now what I want to say is this Barmpalias Lewis-Pye theorem. And the theorem is more about computability. So it's unfortunately, it's more or less the classical version is Lebesgue integration, Lebesgue monotone differentiation theorem. but let me still things. So there are lower semicomputable reals, which means that there is a sequence A1, A2, which computable and increases and converges to A. And the theorem, imagine that there are two lower semicomputable reals, A and B. So there is a sequence which converges to A and a sequence which converges to B. And additionally, we assume that A is Martin-Lof random. And then the claim is that there exists a limit, B minus Bn. So the speed of convergence is quite related. So there is a limit exists. This is what is this Barmpalias and Lewis-Pye.
And B is not necessarily random.
B is not necessarily random. In fact, if B is random, then this limit is non-zero. Oh, because we can reverse the ratio. And if B is not random, then the limit is zero.
Oh.
But it always exists.
Mm-hmm.
And there is a previous result which says that under the same conditions, this sequence is bounded. Is a kind of previous result. It's not that difficult. And it would be nice to have a geometrical proof that Ivan believes that there exists one, but that's I don't know it. But there is a result. So we need to show that for every alpha beta, this B minus Bn, the sequence crosses this gap alpha beta finitely many times. This is just what we need to prove. Yeah. Hoля, is it okay?
Yeah, the statement is okay.
Statement is okay. And then maybe you can guess how we will prove it. So we need to prove in a contraposition way. We need to prove if for some alpha beta, this crosses alpha beta infinitely many times. And then we need to prove
A is non-random.
Of course, that A is non-random. Okay, so now how we prove this? You can say it next thing. So we can draw a picture. Why cannot we draw? We can draw a picture. The picture is like this. We have AB. And we have the sequence AI, BI, which both increase somehow and converge to alpha beta. And we need to show that if this, let me try to draw, if there is some very small, even thin alpha and beta gap, and this thing crosses the things infinitely many times, then alpha is not random.
A is not random.
A is not random, sorry. Alpha is slope, yeah. A is not random. Значит, как же нам доказать, что в этом случае оно не случайно?
Ну, мы там знаем про интеграл ведь.
Да.
Что-то.
So for every x, we consider all possible things, all possible cones starting from every xy. And for every cone, we consider the number of bishop crossings. No, for this cone it's 0, of course, but there will be something for cones which start more or less here. So we consider the number of bishop crossings starting at point xy, and then we make maximal over y of these things.
Sasha, and it is not clear. So you take this, how it's a broken line?
It's a broken line with infinitely many parts.
Chain, how you say?
Ну, ломаная, я не знаю, как сказать. Broken polygonal line. No, it's not broken, it's continuous, it's not that broken. but it's, how do you say it in English? I don't know.
Okay, so we consider this line, and this line doesn't depend on capital A, right?
No,
I mean,
it's some line. No. So the line is just a line which depends not only on the capital A but also and capital B, but also on the sequences AN and BN that converge to A and B. So this is a line which determines A.
I mean, but for a while we forget about both capital A and B, and we just consider this line.
We just consider this line. It determines A and B, but we just consider this line. And for every point xy, even not related with this line, we just count the bishop crossings.
The integral is bounded somehow. Why it's bounded? Because
so for every point we have some point TB. Some for every point xy we have some number of crossing.
B comes from bishop, not from the
bishop. Yeah.
Okay, and what do we know about the integral of this function?
No, we know that the integral of this function, integral over x. Integral over x. This function t of x is bounded by O alpha beta of variation of curve. Not variation, total, it's variation of a function, but total length. And total length of our curve is finite because it's just some curve in going monotonically right and up.
But it may be infinite.
No, it just converged to AB. So the length, total length is the number. Total length doesn't exceed the sum of this and this.
Okay. And then this implies that the number of points where t of x, I mean the measure of the set of points when it is larger than capital N is very small.
Yeah. And when this maximal is larger than capital N, is very small, and we know that at point A,
it is larger than N.
T of A is infinite. And so it is in the set when which has small measure, and this set is computable because is effectively open because of course if the number of intersection is greater than k, then at some finite level of construction of the curve, we see that this number is greater than k.
Меня вот что во всем этом смущает, что мы зафиксировали АН, БН, да?
Да.
Чтобы все это проходило. Последовательность.
Да.
Самое мы зафиксировали А. А потом строим покрытие какого-то множества. Что же это за множество? Оно же зависит
от... Мы хотим покрыть... Нет, в сущности мы хотим покрыть наше А. Но
покрыть,
всего лишь нам хотим покрыть точку А, больше мы ничего не хотим.
Ну, покрыть точку А.
Но мы хотим ее покрыть чем-то, которое эффективно открыто. То есть в момент, когда мы покрываем, мы не знаем точку А. Мы не можем сказать, что мы просто покроем ее там интервалом длины меньше 1n.
Ну да. Может
Поэтому
быть,
мы покрываем точку А множеством тех иксов, для которых для некоторых игроков у нас больше, чем n пересечений.
Хорошо.
И для этого нам не нужно знать А и Б, нам надо знать только кривую.
Можно считать, что АН, БН фиксированы, но вообще это не проблема, потому что их счетное количество таких АН, БН.
Да, мы можем их вычислить, и мы смотрим все больше и больше интервалы до все больше и больше точки АН, БН. И для каждого из них смотрим, где находятся точки, у которых больше, чем сколько-то пересечений.
Ну, в общем,
и это множество растет со временем, но все время его мера остается малой. То есть это ровно то, что нужно по Мартин-Лёфу. Получаем покрытие точки А, системы интервалов, перечислимой системы интервалов малой меры.
Угу. Да, все понятно.
Вот. Ну, я надеюсь, что вы согласитесь, что это рассуждение. I hope you will agree that this argument is simple, especially if you try to read the original argument of Barmpalias and Lewis-Pye, which is completely unreadable. And there is even a simplified version by Miller, which some people claim they understand it, but I was unable to understand it. So, but now the achievement is first there is a combinatorial inequality of bishop, and it immediately implies, more or less immediately implies this Barmpalias thing. And also is Misha Andreev, who explains the combinatorial inequality of bishop in very simple way. And it's a Muchnik principle. If a proof consists of several simple steps, it is simple. But here we have only 2 steps, so I guess you should be more or less okay with this principle.
Yes.
Okay, that's what I wanted to tell you, and even if it was not that clear, it was in time. Есть такой принцип, что если рассказ непонятный, то хотя бы должен быть коротким. Ну, я не знаю, я надеюсь, что может даже было понятно, но, по крайней мере, мы вовремя все успели.
Да. Okay. Thank you very much.
Do we have some questions? For example, what will be next time? Is there some idea?
Ну, я мог бы предпринять очередной этап мучений. То есть
Да, и новый вариант теоремы, это самое состояние дел с теоремой Гудмана-Штрауса.
Да. Но я уж не рискую, честно говоря. То есть
но если стало проще, как ты говоришь, может быть, можно попробовать?
Проще. Не давайте попробуем. Я думаю, что результат будет такой же, но, по крайней мере, формулировку люди поймут. Теперь формулировка простая. То есть я добился, так сказать, этого уровня Адяна, что формулировка простая.
Да. Okay, so this is about Goodman-Strauss theorem about substitution tilings, which are finite, which have local rules.
All right.
Okay, but if you decide that there are some other things, maybe you can tell something else, or someone else can tell something else. But just let's if in 2 or 3 days they are better. If you think you can find something better, then you can find it.
Okay.
Save yourself from this. And why you're with the crunches? Почему у тебя какой-то костыль на экране? Это так должно быть?
Ну как же, я же еще это самое, реабилитацию не закончил. Ну, там, 3 месяца только прошло.
А, нет, ты вроде сидишь сейчас, это самое.
Ну что ж мне выбросить его?
Нет, ну так это самое.
Зато он при мне
Да.
лежит. Ну ладно, я-то пойду.
Ладно, но реабилитируйся тогда в глазах
Хорошо.
мировой общественности. Ладно.
Окей.
Окей.
Bye.
Bye.